Alrighty, one last topic I want to cover in this chapter on the family of stars and the observational properties of stars. Is a technique that is rapidly going to become almost obsolete, at least for stars in our half of the galaxy. It's called spectroscopic parallax, which is a misleading name because it's not a parallax at all. Remember, geometric parallax, the measurement of stars due to their shift in position caused by the Earth's orbit around the Sun, is the only direct measure of a star's distance. Unfortunately, because of that, astronomers started using the word parallax as a generic term for a distance estimation method. And so instead of calling it spectroscopic distance estimation, they called it spectroscopic parallax. But it's not a parallax at all. It's just an indirect way of estimating a star's distance by classifying the stars. Now, here's how it works. It's kind of like taking a political poll. When you take a political poll, you don't call up every single voter who's going to vote in the election. You get a sample that you think is representative of the voting public as a whole. And you use that with some, plus or minus error to say who's ahead of whom in the election. And they're usually relatively accurate, but there is some uncertainty, of course. And in the same way, this is a more uncertain way of finding the distances to stars. But it's the only thing we had up until recently to get us beyond a few hundred parsecs. Geometric parallax from Earth would only work recently, again, up until about the past 15, 20 years or so, would only work until a few hundred parsecs from the Earth. And after that, you were sort of out of luck as far as directly measuring distances to stars. Well, that is changing. That changed, first of all, with the Hipparcos satellite in 1990, and it is changing as we speak now with the Gaia satellite, which will basically take the distances to millions, literally millions of stars in our half of the galaxy, and we'll be able to give pretty darn accurate distances all the way to almost the galactic center, which is 30,000 light years away. So it's truly amazing. But before we had that, we had to somehow find our way to do estimation of distances to stars that were too far away for parallax. So after that very long-winded introduction, let's try to figure out how it works. If you put the stars of known distance on an HR diagram, you have stars of known distance, you figure out their brightness, their luminosity, and you figure out their spectral type. You find 90% of them along the main sequence, but you see a smattering of giants, a smattering of supergiants, and a smattering of white dwarfs. Okay? What you do then is you assume that the stars that you know the distance to are nothing special. You assume that, like the people you call on a political poll, they are representative of a much larger population of stars in the galaxy. So in other words, the stars that happen to be within measuring distance of the Sun are no different than stars you would find, say, on the other side of the galaxy. And then what you can do is this. You can say, all right, I'm going to take the spectrum of a star to figure out its temperature. So let's say, for example, I find out that it's a B star. Okay, the B star, that's really easy because, well, most B stars are main sequence stars. Now, there are some B supergiant stars, but most are B main sequence stars. And so if you find out that it's a B star, its brightness is probably this. Okay, if it's over here on the main sequence, so you follow the temperature line up, and you say, okay, it's right about here. I know that most main sequence B stars are about this bright, so I sort of read off the luminosity plus or minus a certain fraction. Now, there are B supergiant stars up here somewhere, and so it might be brighter than that. Okay? There is a way of figuring out, though, whether it's a supergiant or a main sequence star. Now, let's say we have a K star, a fairly cool star. A K star could be a main sequence star, or it could be a giant star, or it could be a supergiant star. So what do I estimate for its luminosity? It could be less bright than our sun. It could be 100 times brighter than our sun, or it could be tens of thousands of times brighter than our sun if it's a supergiant. So what I have to do is figure out, okay, I know its surface temperature, but I don't know whether it's a main sequence giant or supergiant. Luckily, the spectral lines will also be able to tell us that, because it turns out that main sequence stars, because they're more compact, have thicker, more smeared out spectral lines. I'll show you an example of this on the next page. Supergiant stars, on the other hand, are so bloated and low density that the atoms in the outer atmosphere of those stars don't interact much, and therefore the spectral lines are very razor thin. So you have razor thin spectral lines here. You have thick smeared out spectral lines here because the atoms in the atmosphere of the star are bouncing against each other quite violently. And in the middle you have giant stars, which are thinner than main sequence star spectral lines, but not quite as razor thin as the supergiants. Okay. By doing that, you can say, okay, it's a K star, it's a giant K star, and therefore most giant K stars have a luminosity of about this, whatever that is. And so you can get an estimate of the luminosity, and once you know how bright a star is, you can adjust for how bright it looks and figure out the distance. So by classifying the star, you have a rough idea of how bright it must actually be, and then you adjust for distance to figure out how far away it must be. Now this is much more uncertain than geometric parallax, but up until a few years ago, for many, many stars, it's all that we had. And it's still something that will be used for stars in other galaxies or in parts of our galaxy that are a little too far away to use direct measurement. Okay, so let's just go through this. The method: assume nearby stars are typical of stars throughout the galaxy. Again, very similar to a political poll. You assume the people you're talking to are not anything special. They are typical of your typical voter. And people who do political polls they do their homework to make sure that they're getting a good diversity of voters that will match the numbers that are going to be showing up at the polls. Then you find a distant star's surface temperature from a spectral type using its spectrum. And then you determine whether it's a main sequence giant or supergiant by using the broadness of its spectral lines. Here's a picture of this. Okay, this is a supergiant star, which has a very, very skinny line. Okay, this is a main sequence star, which has a very, very thick line. Okay, the phenomena that makes it thick is something called pressure broadening. Because a main sequence star's atmosphere is under much higher pressure, the spectral lines get smushed out, and you get a much broader line. And a giant star would be somewhere in between. Okay. So a main sequence star has broad spectral lines. Giant and supergiant stars have narrower lines because their atmospheres are lower density and lower pressure. And then you estimate the luminosity by fitting the star to the HR diagram. And once you've read off the luminosity, you can get an estimate of the distance to that star. Okay. So you estimate the distance by comparing the estimated luminosity with the star's observed brightness. All right, and that's pretty much it. So I just thought I'd add that in because it's a very interesting and very clever way of figuring out the distances to very distant stars, ones that were up until very recently beyond the measurement capabilities of geometric parallax. And it's just a really kind of a neat application of science. Okay, well that's it for this chapter, and we should now go on to the next chapter on the formation of stars and the lives of stars, and we will be talking about the birth of stars, basically.